if the first part of this video is a little boring, as I'm still getting organized here. I've got my demos to set up here. All right, and so maybe as a bit of fun, before we get too far ahead, let's start with a demo today. And then this is one I didn't necessarily have time to get to last time, which I wanted to. So I'm gonna get started with that. And I'll bring the Zoom camera in here. Maybe it's a bit of fun before we get too far ahead. All right, let's start with a demo today. Then there's probably some mode, and I should take the time to figure it out, but I don't know if you realize this about teachers. We're always just barely hanging on. All right. So we're going to try and look at this demonstration right here. I've got power supply. I'm going to crank it. I'm going to connect this power supply to this device right here. I'll give you a view of it in just a sec on Zoom. Oh, we're good. We're good. There's no short yet. It's not actually connected yet. All right. Sorry, I was like, oh crap, I forget I've got a large power supply here. All right. So what we can see here is there's a piece of metal right here and on the other side as well. And in between, I don't know if you can see, but there's a bunch of magnets right there, and they run the whole length of this thing. So the idea is there's a large magnetic field, and I just can't remember if the magnetic field is pointing this way out of the board or this way into the board. And so now what I'm going to do is I'm going to turn it this way. Sorry for the squeak. Make sure that shows up a little bit. Okay, so you can kind of see that. So now there's no current running, right? You should see zero current. Yeah. And then can they see that? Yeah, they can. So the idea is when I put this on here, this can actually connect the two rails and allow current to flow. So now what I'm going to do is I'm going to pull this. Now it's disconnected, so I'm going to put it on here. There should be no current. When I plug it in, we should see current flow. And actually, it's a little bit easier for me to plug into that one. So give me a sec. So now what I'm going to do is in just a minute, I'm going to plug this in. And I want you to tell me what should happen here. Well, actually, let's just see. I don't know. What do you think? What should happen when I plug this in? There's going to be current flowing through this. It's going to roll. Now, I don't know which way it's going to roll. But I was hoping we could watch which way it rolls and then figure out which way the magnets are oriented. Got it? So I'm going to plug this in. Maybe. Okay. So do you agree there was a force this way? So let's do a quick sketch on the board. It's kind of a fun warm-up, right? So from a top view, what did this look like? We had a rail here and a rail here. Which one of these was plus? So if we look at this from a top view, it looks like the black was on top. So this was the minus lead, and this was the plus lead, right? And then at some point, we saw there was a rod here, and we see that there was a force this way, right? So in this case, if there's a force that way on the rod, what direction was the B field? What do you think? How would you approach that? Okay, a right-hand rule. Do you happen to have an equation we could write down that comes to mind, which would help us think about the right-hand rule, or what would you do for the right-hand rule? I guess just tell me that.
Towards the force, we pick our fingers towards where you said it's either out or in.
Okay, let me write that down first. Expect, that's not a very good pen. Expect B external is either out or in, right? Because we said it was going to go either out of the board or into the board. Okay, cool. Yeah, yeah. What else?
And then probably just trying to, I guess, not mix and match, try to troubleshoot until you can find something.
Okay, yeah. So how do we do the right-hand rule for this force? Do you remember? It was, okay, so yeah, let's, in this case, I heard Q V cross B. That's one you could use. Okay, what was the one that had to do with current?
With the IES cross.
Yeah, and in constant, I could change the DS integral to just a. So if you have a uniform B field and uniform length vector, right? Well, in this case, what direction is current flowing? Here's the rod, right? What direction is current flowing? It goes from plus to minus, doesn't it? Now, the electrons would move downwards, right? Electrons moving down will be analogous to current flowing upwards. Negative going down is the same as positive going up, so to speak. All right, so now which way is the B field? We line up our fingers with what? With what? Current. Yeah, we do the, now we got our, now we can see the right-hand rule that we need to do. It was this goes to that. So let's try it. This into the, oh, I got it. So in this case, do you agree the B external is probably into the page? All right. Remind me, is the top surface of this thing a north pole or a south pole? For this one, it helps to have a side view. For this side view, right? Here's our two rails. And the idea is the B field is which direction? Actually, I'm going to draw a pure side view just because it's kind of hard for me to do this. So let's just draw one of the rails. There's one of the rails. And I think we are looking at the positive rail, right? Which direction would the B field point in the side view? Downwards. So which face of the magnets in here, like let's say this is coming from a magnet, which face is going to be north and which face is going to be south? Do you remember? If it helps, I'll draw a little bar magnet here. North and south. Do you remember which way the B fields point? Out of north and into south. You're going to see this picture a lot. So based off that, the top part of this magnet is south. And what they do is they put a whole bunch of south poles on next to each other, right? Take a whole, and then there's a whole bunch of norths on the bottom. All right. Feeling pretty good on that? That's our warm up for today. All right. All right. So that was magnetic force. That was last time. I just didn't have time to show you that one, so I thought I'd whip that out. All right. It's kind of a fun way to start class. All right. So now, where are we at? We're now up to the Biot-Savart law, or the next chapter, which is chapter 29, I believe. Okay. All right. So what I'd like to do is get into that. Now, before we do that, I'd like to mention a few things about the schedule and where things are at in the class. So right now, let's see, the test is next Monday, right? And so we're starting our big oral presentation lab this Thursday. So we're going to acquire data this week. Next week, I'm going to help you prepare the presentations. The following week, you're going to actually present them. So believe it or not, after that, there's only one more lab that's required. And then the other one is the makeup lab. So, man, the schedule is gonna come furious here. I don't want to spend too much time on that. Basically, I'll leave it at this. Check the schedule. If things are going to start coming fast, including the exam next Monday. Now, to that end, I wanted to address any questions you had. So at some point today, maybe what we'll do is maybe the last part of class, if we get to a good spot where we can stop, we'll do the rest of class with questions. And then next time in class, I want to start the class with any questions. So this may not make for the best YouTube videos for posterity, but who cares about everybody else? Let's focus on your survival this semester. All right. So I want to try and get through some new topic and then go to questions, any questions you have. All right. That said, was there anything that jumps out at you before we plunge into the Biot-Savart law right now? Anything that you're wondering about, or it could be, anything about the class? Just a chance to talk about that. Anybody on Zoom have any questions as well? Okay, and we've got more time on Wednesday to discuss this as well. Regarding this section, right? We're in chapter 29, right? Okay, so we're going to be in chapter 29 for 3 class days. So check this out. This week, you don't have to do any homework on this chapter, right? The idea is, let's see, we have today's lecture, Wednesday's lecture, and then next Wednesday's lecture as well, because we're not going to have any time for lecture during the test day. So hopefully what you can do is learn as much as you can about this stuff. The stuff that we're going to talk about from this point forward is not on the test, but it relates to it, so it's good practice. And then hopefully, as soon as the test is over Monday, you'll be super stoked to start working on the homework. All right. And as always, if you haven't started planning your schedule towards the rest of the semester, you should probably factor in when I'm going to study for which class at what times, and like pencil in times and write it out, because it's going to get out of control. There's not that many weeks left. Thanksgiving's one of them. Oh man, it's gnarly. Any questions? Let's get to content, and then that'll help us get to questions later. If I went too fast, just let me know, and you can bring up the question after we get to the break or something. All right, not like that. Let me get my. What happened to my? The cloth. I wonder if somebody took it. Just sitting up here on the whiteboard. Great. I'm like a whiteboard picky person. I like my whiteboards perfect. All right, whatever. We'll do the best we can here. All right, whatever. Okay, Biot-Savart law. Page 151 in my book. All right, 151. Now, previously we talked about electric fields, and so I want to bring up a little bit here just to kind of give you a feeling for this. We did electric fields, and probably you know the equation KQ over R squared and the R hat, which is equal to KQ R vector over R cubed. Remember that from the beginning? And we would talk about, oh, here's some charge, there's an R vector here, and there was a point P. And then do you remember we would sometimes take a rod and we would build it up out of point charges. You know what I'm talking about here, kind of a little bit? So hopefully a review. And then what we would do is we would slice this thing up. There's a small chunk dx, and we could say, oh, well, this is x. And so then this would be the R vector. Remember how the R vector would go from the source to the point of interest, and I could figure out the electric field at this point? Well, if we're talking magnetic fields, it's similar. Now, what I'm going to do is I'm actually going to talk about dV instead of E. You might recall that, well, I could change this really quick. Do you remember we called this dE if we changed this to dQ? So I'm just going to do that really quick. So you could get the electric field from one contribution and add them all up. Why is this critical? Well, imagine we're doing something like this where you have a wire, right? And there's some wires here or something. I'll pick that up hopefully. But the idea is there's current in this segment and this segment and this segment. Naturally, all of our wires have the current distributed, sort of like a distributed charge network, right? So we've got to deal with this, and I got to pick this up before I lose it. Step on it and break it. So the idea is if I wanted to do something equivalent, I can't just have a single point charge with a current. Usually I have chunks of it, and I have to split it up into chunks. Sorry. Okay. All right. Well, now the equation that I'm going to write down, you could just pay attention. The equation is actually on the next page, but I'm going to review it again a second time. So you could just watch this first time and not take any notes if you want. Okay. There's going to be some constant, like before we had K. Now our constant is going to be mu naught. Mu naught is 4 pi times 10 to the minus 7. And I don't remember the units. Did I write that down somewhere? Oh, it's probably on the back. Tesla meter per amp. So that's just a constant. That's like our constant K. All right. Q was the source of the electric field. Now we're going to have current, right? Current is the source of the magnetic field. All right. And then there's got to be some sort of association with distance, right? You would think if you're far away from a wire, there would be a small amount of magnetic field. So here's where it gets nasty. There's a cross product in there. All right. So the B field or magnetic field, you're going to hear me say B field a lot. When I say B field, I just mean magnetic field. The B field relates to a constant, the amount of current, the direction current is flowing, and how far you are from the wire. So all these pieces tend to make sense. In practice, we don't want to get the contribution from one piece of the wire. We want the entire wire. So B is equal to the integral of dB, right? The total is the sum of each contribution. Well, in this case, it's just going to be, some of this stuff is going to pop right out. Do you agree? This mu naught I over 4 pi constant. Generally speaking, if we're talking about current in a wire, right? If I talk about current in the wire and the current is like 6 amps, it's 6 amps no matter how screwy this is, right? The current, this is just the amount of amps flowing. That doesn't depend on this. DS is tricky. That depends on which way the wire is bent. Okay. So these are all constants. That's why I separated them out. Mu naught I over 4 pi. Then we got to do an integral of, and then what do you bet I'm going to do with this r hat and r squared? What do you think I'm going to do? R cubed and r vector, right? Because r hat over r squared is equal to r times r hat over r times r squared, which is r vector over r cubed. Everybody okay with that? So that's what I did here. This is the practical way we do it. Sort of like when we were doing all our coding, we always use r vector over r cubed. All right. Now, on the next page, we're going to do a specific example and walk through how you use all this. Before we get to that, I wanted to talk about the direction, right? And here's why. When we're doing long, complicated calculations, like perhaps how when we did electric fields, when we did long calculations with these, we usually checked two things at the end. What was one of the things we usually check at the end of a problem? What's that? Oh, okay, three things. That was not one of the ones I was thinking of, but you're right. That is one of the things we did all the time. Like, how would it behave if you were infinitely far away? You're absolutely right. But what else? What are some other things we check with every physics problem? Check the units, right? So if we're going to want to check the units, I'll explain that in a minute. I'll give you a reference formula. But when we were checking units on electric fields, we basically say, is K on top? Is Q on top? Do I have meters squared on bottom? Remember that? So with these ones, we're going to say, here's a famous magnetic field. Let's just get the magnitude for right now. So we're going to have mu naught on top, current on top, and it turns out meters on bottom. So that's how we're going to check the units. This formula is written on your equation sheet. We're going to derive it next. So you don't need to really understand where that came from yet. The point being, basically, this is for our unit check. Mu on top, I on top, meters on bottom. Got it. If you want, I guess you could just see that right here, right? Mu naught is sitting right here. Well, we better have amps on top and meters on bottom if we're going to end up with Tesla. Okay, so there's your units. What's another thing that we check? Do you remember? When we're doing electric fields and electric forces, usually we would think about it, which way it should point. Do you agree? We'd say like, well, if these are both positive, they should repel. Or if this is positive and this is negative, they should attract. So we want to have some way to check that. Well, there is a direction hidden inside of here. And I'm going to show you that right now. Let's imagine we have a segment of wire right here. This is just a small segment of wire. All right, and let's assume current is flowing upwards right now in this segment of wire. So that's my ds vector is probably dy in the j hat. Okay, it's a small length in the y direction. Current's flowing upwards. Again, we're going to redo this in a minute. But let's say I'm sitting over here at some point P. All right. If I'm sitting over here at some point P, well, what is the R vector? Do you remember? Which way does the R vector point in general? From what to what?
From the point of interest to, wait, is that backwards?
Whoops. I'm trying to block it with my head. From what to what?
The source to the point of interest.
Source to the POI, not from the POI. So that means this is our R vector. Agreed? Now, in general, we have a cross product here. The output of the cross product is always related to the inputs using our standard right-hand rule. What is the standard right-hand rule? Line up your right hand with what? The first. Curl your fingers to the second. Thumb lines. So watch this. I got to line my fingers up with ds. Now I'm going to curl my fingers to R. Is that correct? No. Is that correct? No. Is that correct? Yes. What does this mean? ds goes to R means the B field is into the page at P. You see that? Now, in practice, I have a couple of other right-hand rules I want you to learn, and I've mentioned these at the top of the page, so I'm going to go over these. All right, so let's go to another board here. Unless anybody has questions about this before we move to the right-hand rule practice. I'm just going to show you some more rules. All right, and remember, we're going to come back to this a second time. All right. For any time you have a long straight wire like this with some current flowing, here's the right-hand rule to get, and actually let me scoot it over a little bit. What I want you to do is grab that wire, and you don't need to write this down because this is all on page 151. Do you see it there? Grab that wire. I'm going to say that over and over again. Grab that wire. Align right thumb with eye. Fingers curl in direction of B. All right. So grab that wire. Grab it with your right hand. My thumb is pointed in the direction of current. What direction is the B field on this side of the wire? Into. How about on this side of the wire? Out. Is that for real? Do you think this really happens? I wish there was a way we could show this. All right. Now, what I've got here is a long skinny wire, and let me see, where's my zoom camera? Hold on, let me see how this looks on Zoom. Okay. All right. So now, I don't know if you can see this, so I'm going to pull this off of here. Our claim is that we expect the B field to look something like this, where it's curling around in circles around this wire, right? Think about it. That's what I'm trying to show up there. As I grab this wire, I expect the field should point in different directions. Like this, around in circles, right? So what's a way I could prove that to you? Any guesses? How can we see the direction the field is pointing? Get that in there. Any guesses? What's something that demonstrates the direction of a magnetic field in the real world?
Magnets.
Okay, cool. How do you know which way you're going if you're hiking around in the woods?
Compass.
Points north.
Compass, which is a small magnet. Absolutely. So now I don't know if this is going to show up at all. So I'm going to try and just kind of manipulate it. Apologies if the Zoom doesn't work, and you guys may want to stand up. Whoops. Okay, I got to tilt it just a little bit less. All right. Now, right now, we see a bunch of compasses on there. Do you agree? And can you on Zoom see that at all?
It's a little far away. Is it possible to zoom just slightly, or is it at max?
I'll find out. Okay. And then what I'm going to do is I'm going to connect that wire to the power supply, and I'm going to crank it. Can you see him at all now?
Yeah, that's better.
All right. So I'm going to connect this bare wire with the power supply. Now, all I've got here is I've got some glass just to make sure the wire is straight. And notice this is still the wire. I'm just trying to use this so I can make sure that the wire is not dangling. Now, clearly there's different segments of wire here, but this is the main one that's affecting it. All right, because that's the only one that's close. So now, whoops. Help me out. Plug this into there carefully. All right, it's not plugged in yet, so you don't have to worry about current or anything. I just can't reach over there, you know what I'm saying? Thanks. Okay, that was it. Let's give him a round of applause, ladies and gentlemen. Very good, very good. All right. All right, here we go. All right, so there's gonna be a large current. If you want to come up, you can see it. Ready? Here we go. Ready? 1, 2, 3. Oops. You see the compasses aligned? Do you agree they're curling around in that fashion?
Yeah.
I can pull this out right here. 7 amps of 8 amps, that's a lot. Now what I'm gonna do is I'm gonna flip the polarity. Just to prove to you that it's really this wire doing this. Notice they go the other direction, right? And so we see these aligned. Now notice not all of the compasses are turning because some of them happen to be already aligned. So we're seeing that this creates a magnetic field which could cause these compasses to align. Is this a strong field or a weak field? What do you think?
Seems pretty strong, right?
Extremely weak. It's barely able to turn compasses and not much else. So this is one of the things. This would be one wire by itself is not going to produce a strong field. Usually what we do is we wrap things over and over and over again to make it stronger. Imagine if you took this one wire and looped it 200 times, the field would be 200 times stronger. So even though this looks strong, it turns out it's incredibly weak. All right, go ahead and grab a seat for a minute. All right. Does that make sense, Christian?
Yeah, I'm just like thinking now, if we put a compass next to like an outlet or something, does it move if there's a connection or voltage and current and whatnot?
If only we could discuss that next week. Is that cool? We can save that for next week.
Yeah, it just got my, brain going.
How about I give you this hint? Let's say I have these two wires. Can you see this at all? Do you see a red and black
I can see
wire?
it.
If I put these two wires right next to each other and I run current one way through one of them, but the other way through the other, do you agree that's almost like two currents canceling each other out?
Yeah.
And so that's why you're not going to notice a strong effect most of the time with your power cables and such. Because
Okay.
they set them up to either have the current run in one and back the other, or on coaxial, so down the center. And so what do you bet there's going to be a magnetic equivalent of Gauss's law where we could study that next week or Friday, or I mean, whatever day it is. All right, is that good for now?
Yeah, thank you.
Yeah, usually you try to design your wires in pairs to avoid the issue that you just discussed, creating massive amounts of magnetic field in regions you don't want. Cool. All right, nice. Let me see, where are we at? All right. Oops, I think we're on board 6. So this is the grab that wire. We see that seems to work. Agreed? That's all that was. Grab that wire seems to work. Well, what if we have a loop of wire? All right. So what if you have a loop of wire like this? You have a loop carrying current, and let's say it's going this way. All right. Here's my claim for this. Curl right, and this is on your handout, right fingers in direction of current. Thumb indicates direction of the at center. Okay, so we're going to try and look at a loop of wire. And what I want to do is there's a subtle difference here. With this one, with straight wires, you grab that wire, your thumb, B. With this one, you curl around in the loop. So notice with this one, when I curl my fingers in the direction of current, which way is my thumb pointing? Out of the page. So that tells us that the B field at the center is out of the page. Does that help? Now, if only there was a way to see if this is true or not. Let's see. Okay, Okay, this is gonna be subtle. I think if I do just enough, I might be able to angle this. It's another one of those ones where you may want to stand up here in a sec as I get this fired up. Shoot, I need something else. Need another shim. How about a remote control? There we go. All right, can you see that at all on Zoom? And you guys might want to stand up again.
Yeah, it looks.
Okay. Can you see this iron I'm sprinkling on here? These are just iron filings, okay? It's like, let me get this stuff out of the way. Now what I'm gonna do, turn this down before I forget. So I'm gonna plug into this coil here. Oops. All right. All right. And now, when I plug this one in, we're not getting much current. We don't see much going on. This thing can handle 2 amps of current. So we're going to use a lot less current now. But because this has several hundred turns, we actually get a stronger field. You see it starting to form already? I do. You might not, but watch this. I'm tapping the box a little bit. And by tapping the box, that kind of allows the magnetic filings to jostle and align. Look at this. You see the pattern for me? Okay, come over and see it. Isn't that cool looking? This is like one of my favorite patterns. Now I want to point out, I don't know which way the current's flowing, but let's just pretend it's flowing this way, right? It's going this way. So notice the B field tends to line up this way. See how it's lining up in the direction we just described by the right-hand rule? Close to the wire itself, do you see it doing the grab that wire? So like right here, it's doing grab that wire and grab that wire, and we see the circles. But right in the center of this thing, it's almost uniform, right? I don't know if you can tell it. This looks really cool. I don't know. That's a lot of work to show some filings, but yeah. Any questions about that? Can you see that on Zoom at all?
Yeah.
Yeah,
Does that help?
it's pretty cool.
All right, that's about as much as I can do on that. So the point here was just that, okay, these right-hand rules are legit. Okay, grab a seat. All right. So now, what have we discussed here, basically? We are now ready to start doing some work. We've discussed that there's electric fields and there were some calculations. We see that there's an analogous type of calculation that requires a cross product and right-hand rules. But we can basically do the same kind of math that we did for these, except we have to do a cross product first. We saw that there are some right-hand rules for checking your direction for straight and curve. Whoops. All right. So now let's go to the next page. Hopefully you can remember this as we're going on. You're going to forget it, but hopefully as we do it over and over, we'll get to work here. So I'm going to look at page 152. It's the page that has problem 29.1. So if you have an older edition, look for problem 29.1. You should see procedure for doing Biot-Savart law. Okay. This work that we've been describing here is total BS. Biot-Savart. All right. All right. My French is terrible. I'm not even going to try to be any better. Okay. Sacre garçon, more wine. Okay, that's the best I can do. So I'll catch up. Give me a second. Read through that checklist. Let me get the other board too. Whatever. All right, and so rather than just, is that glare killing you guys? A little bit? I'm gonna shut this door a little bit. Still even crack, but I can see a little bit better. All right. So I'm going to try and do problem 29.1. And I'm going to try to follow the instructions in this checklist, okay? So if you want to race ahead, you've got the solutions. Don't wait for me, okay? So in this particular case, we've got a long straight wire. We're told that this distance is what, L1? And this distance over here is L2. Apologies for the small font there. Sorry, it's getting cut off there. Okay. Now, there's a point P located right about here. Maybe I'll make it a little bit farther just so I have some room. Okay. Okay. Our goal, we want to determine B at P. Okay. The idea is in the previous chapter, we were constantly given a value for the magnetic field. Now we want to derive the magnetic field. So we can figure out this B field, then plug that into a force equation. What's the first step? What's the first thing I have to do? According to the checklist. Draw the perpendicular bisector. Okay. So let me ask you something. That's going to cut this wire in half, approximately. Is that a perpendicular bisector? No. So the crucial thing about the perpendicular bisector is basically you have to go from the point to the wire and it has to be perpendicular. That is required. It doesn't matter if you cut it into equal pieces. It matters that it's perpendicular. That's why we call it a perpendicular bisector. That's the first crucial step. Everything depends on that. Next, what do we do? Draw a coordinate system with the origin there. Okay. There's my coordinate system, and here's my origin, right? Gesundheit. Next, draw DS. Okay, I need to pick an arbitrary point on the wire. How about right here? First quadrant is usually pretty good. So there's my DS. Okay, that's DS. You guys see that all right? Sorry if it's a little small. You guys can see okay? All right. There's that. What's next? Draw the displacement vector. Okay. Which way is that going to go? Nope. Source to P. So this way. That is your R vector. Okay. From the source to the point of interest. Next. Oh, figure out the R vector. Okay. Well, in this case, I think I told you this dimension too, didn't I? Isn't this side, is this length A? Yeah. All right. So what's the R vector? How much does it go in the I hat direction? X. So notice you just knew that this distance right here is probably distance X, right? We have to define that parameter, right? You choose where DS is, so you got to tell it how far that is. So the R vector is going to be what? How much I hat, J hat? Negative X I hat.
Negative AJ hat.
Negative A J hat. Because A was this distance. Yep. Hey, what's the magnitude of that?
Square root of x squared plus a squared.
And then instead of writing square root on these, what do I usually do?
Raised to the 1/2.
Yep, because that's gonna be convenient when we plug it in. Square root is totally legit, totally acceptable. All right, now what? You know what? We're ready to shove it in. Do you agree? We don't need to get R hat? Okay, so that's the trick. I do want to mention, in this problem, what is ds? Which direction was current flowing? Did it say?
I hat.
Current flow is this way? So what is ds for this particular problem?
dx.
dx I hat, right? All right, so now we're ready to shove it in. The magnetic field is the sum of the contributions. Well, we know there's this mu naught I over 4 pi integral, right? We need to add up all the contributions of, what was it? ds cross r vector over r cubed, right? So now I'm going to keep rolling. Oops. All right, see you at the end. Anybody can ask any questions at any time if something comes up, okay? I'm just a little slow with all these different colors going. What's that R vectors? There's a negative sign on everything, and then it was. What's my power going to be in the basement now? What is it? 3/2. And then maybe I'll make this clear that that's not a minus sign. All I did was I figured out the minus out of these if they're both negative. Now, I'm going to try and clean this up just a little bit here. What's the first thing I should do when I see this type of problem? Should I do the integration or the cross product first?
Cross product first.
Cross product. In fact, why is that a great idea in this particular problem?
The I hats will cancel out.
Guys cancel out. I cross I drops. All right. All right. So the I's have it. Oh, and is it okay if I pull this minus sign out front? All right. You can race me now. I'll see you at the end. I'm going to put my negative sign out front. And I'm going to do mu naught I over 4 pi. And now integral. And then, geez, we still got this junk in the basement. I'll just write that. Nothing happens down there. I'm going to put the dx and just leave it out here at the end because that's usually where we see it. What's left? We've already taken care of the minus sign. What's left?
A dx or AJ hat on top. Oh, wait, shoot.
That. Do you agree that's the only piece I haven't done yet? We've taken care of the dx. We've taken care of the basement. We've taken care of the minus sign. We've taken care of this crap. So notice what's left is I hat cross a j hat. What is that going to give us?
K hat.
A k hat, right? Because the A is still there. So the I hat cross J hat gives me K hat. And then there's still an A left lying around. Is everybody cool with that? All right. So to be clear, the portion in this dotted blue line circle came from that. Hey. We're going to do an integral. What might be useful at this point? Some limits and some tables. There's an integral table on the back. Sweet. What are the limits of integration here? Say again. This is what's crucial about that perpendicular bisector, everybody. It's super crucial. Here's the deal. If you want this formula to work, the portions closest to the perpendicular bisector should matter the most. That's why this becomes the origin, right? If this is the point that I care about, shouldn't this piece of the wire matter the most? In order to make this formula produce that physical effect, we need to make sure the origin is right here. Well, if that's true, what's this limit? Negative L1. The limits usually have a negative on one of them. And then what's the other limit then? Positive L2. The idea is this is our zero. These are negative, those are positive. Gosh, what if you accidentally flip it and do your minus signs the wrong way? Are we going to be in trouble? What would happen if you accidentally flipped both of the signs?
It'll change the sign.
It'll change the sign of the answer. How could we ever possibly hope to check this answer?
Right-hand rule.
Okay, I've got a straight wire. What am I going to ask you to do? Grab that wire. That's right. I said it. Above the wire, what direction is the B field? Below the wire, what direction is it? Is our result going to give us that? I've got a K hat here with a minus sign out front. Got it? That's how we use the right-hand rule to check this. Feeling good? At this point, this is easy. It's just a table, but let's do it anyways. And now I'm going to stop color coding. Well, I guess, do you agree I could pull an A and the K hat out? So I cannot stress this enough. Do the cross product first, then do the integral. Otherwise, suffer. Okay? Now, what's left in this integral is dx over x squared plus a squared to the 3 halves. I don't know if you can see it, but do you see a triangle here? When I see triangles, I think trig. When I see calculus with triangles, I think trig sub. Now, we're not going to do the trig sub, but I did it in the solutions. If you want to see how to do that one, it's particularly diabolical. All right? It's one of my favorite integrals. All right? It's a close personal friend. But I'm going to just write it out. The result of this integral table, isn't it something like 1 over a squared? Let me just, it's on the back of the book.
1 over a squared sine theta.
I'm going to get to that in a minute. I'm going to first write it this way. There's this. So far, so good. And then you can plug in these numbers and you got your result. Now, somebody mentioned sine theta. I want to discuss that. Is this still running? Oh, geez. Turned it off. Good. Sorry. Before I do that, any questions on any of this work here? Is that okay? Remember, you got the solutions too. So now I want to talk about a better way. All right. So let's go over to the other board here. I want to look at this. In particular, I want to look at the limits. and how to do this integration. This is our scenario. Am I on the right board? Yes. Okay. Here's our point P. Now, in this case, this x coordinate is negative L1. Over here, this x coordinate was positive L2. All right, that's the two ends of the wire. What is this x coordinate right here? Right in the middle, 0. That's our origin. Remember that? Okay. We set our origin at the perpendicular bisector. Here's perpendicular. All right. Now let's look at this angular. Now in this case, I don't know if you see this, but let's say I call this theta 1 for the first angle, and this theta 2. Let's discuss this. What angle would this correspond to right here above the marker? Theta equals 0. I'm at the perpendicular bisector. I have no angle from it. That's what I mean by it. So just like this is the origin, I'm going to actually refer to this as the 0 angle. Well, take a look. Would this be a positive or a negative angle over here if you have to guess? How about this one? Negative. So this will work out. So now in this case, I'm just going to point out what is sine of theta 1. Well, in this case, let's see. What's the length of this side right here? What was the length of this side?
A.
So what's the length of this side? So sine theta 1 is x over, or well, I guess I should say it's negative L1, right? Over, and if I could, I'm comparing this formula right here to that formula right here. Do you agree the sine theta gives us the same result?
Yeah.
Now, I haven't clarified the A's and how that cleans all up, but it just does. You just trust me on it. Now, look at this. Notice this makes sense only if theta 1 is a negative angle. When you plug in a negative angle, don't you get a negative answer for sine? Remember the first quadrants and stuff like that? If you use a positive theta, you get a positive component for sine. If you use a negative theta, you get a negative value. All right? So the idea is this will work if as long as, again, for straight wires, perpendicular bisector. That's got to be correct. If you screw that up, the whole problem's just toast. Get the correct perpendicular bisector. That's going to be your reference point for positive and negative quantities in your limits. Understood? Now, in this case, I'll just point out, let's do sine theta 2. What do we get here? Wouldn't that be the same thing, but with positive L2? So in this case, hopefully that's still on the board. Yes, it is. So I just wanted to show you that if you use what Jacob said, instead of doing it this way, Jacob, what was the formula that had theta in it? Was it 1 over a sine theta?
1 over a squared, but yeah.
1 over a squared sine theta, right? I guess I should have written that in pink. So the idea here is you can actually do these integrals with the sine theta. Now, here's what I want you to take away from this. Please, 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 on test day, do not waste your time doing all this. What do we want to do is, this was our derivation of it, agreed? You kind of understand it, you see the issues involved in it. You can do it if you need to, but why not? Come on. There's a shortcut right here below the checklist. You see that? What I was going to do is say, geez, come on, why don't we just jump right to this? We could say B is equal to mu naught I over 4 pi A. That's the perpendicular bisector distance. I'll get out of the way. Times sine theta final minus sine theta initial. If you do all the math, that's what it works out to over and over and over again for every straight line segment. The key is you need to know how to draw this picture and whether thetas go down here or up here. They go down here. Got it? Why do they have to go down here? Because that's what gives us the correct results for the limits when we're doing the integral table. Does that make some sense? For straight wires, do this instead. Yes. I couldn't hear you. So here, how do we get the direction? Because that's the next thing I was going to say. You're on it. That's great. Do you agree these two things do not match up yet? This is a vector, this is not. How do you get the direction? Every time. Which grab that wire is a euphemism for right hand rule. Does that help? So I'll call it question mark hat, where you have to figure it out. That's the easy way to do it, in my opinion, once you've practiced it a few times. It's not going to be easy the first 2 times, but by the 3rd or 4th, it will start to get easier. Is this on your test on Monday? No, just a reminder, okay? So you're going to have next week to practice this after the test, agreed? But you can see we're doing a lot of right-hand rules and cross products. This is still good practice. All right. All right. What if you have an infinitely long wire? You might be saying, well, that's pretty ridiculous, right? You don't really have an infinitely long wire, right? But I argue like this. Let's use this meter stick, right? So instead of using this wire, let's use this meter stick. Clearly, this wire is not infinitely long, right? However, in what sense is it infinitely long now? If I'm this far away from it, right? From my eyeball's perspective, it goes as far as my eye can see, right? And so what does an infinitely long wire look like? Well, it's a regular wire, but you're just really close to it. If you're really close to a long wire, we can treat it as infinitely long. Why is that? Well, let's think about it. You had it infinitely long. You have an infinitely long wire. You're basically saying, I'm so close to it that this part of the wire is going to contribute so much that everything far away is negligible, right? The points close to me are going to produce the most field. And if I'm really, really close to it, all those points really far out don't matter that much compared to where I am. Agreed? So now, I like to do things in angles. You agree this would start to creep out here and it would go to forever, right? To be clear, this would keep going forever. This would keep going for really long ways forever. Same thing over here, right? This would keep going forever. That's not the current, that's just the wire, okay? What angle does this look like? Approximately. What is it? No, it's not 90.
It's getting close to 90
It's getting close to, not 90.
or 45.
It's not the number you're screwing up, it's the negative 90. Because this is the negative side because I'm on that side of the perpendicular bisector. You're right, it's going to 90 in magnitude. Do you agree? Does that make sense, Christian? And Christian?
Yeah.
All right. This one is 90, right? So now, what's going to happen in this formula? What is sine of negative 90? We're going to get sine of positive 90 minus sine of negative 90 degrees. Well, what's sine of 90?
1,
1. What's sine of negative 90?
-1,
So we get 1 minus -1 equals
2.
2. And notice our B field. U naught I over 2 pi A. And then I'll call it question mark hat. The idea is the infinite wire, essentially, if you're close enough to it, the angles go to 90, right? Look at this, right? My eyeball has to turn basically 90 degrees to see either end. This is on your equation sheet. Is that good? That's an infinite straight wire. Whew. So far, so good? Well, this is insufficient to model reality. We can handle straight wires. What's something else we might need to do? Circles. That'll be what we do right after the break. Okay? So we'll handle a circular wire after the break. Then we'll maybe do one example. I'll show you some shortcuts. Then we'll just do questions. Cool? All right, let's take a break. Any questions out there on Zoom land while we got this? Oh, question?
Can you show the right hand rule for the R vector on that?
For the right-hand rule for the R vector? You mean
Just the.
for this right here? Show this right-hand rule?
Yeah.
You feeling brave?
Yeah.
Come on up. Okay, I'm gonna help you.
Alright.
So now we're trying to figure out the direction of this right-hand rule with this using this picture.
Yeah.
Line up your fingers of your right hand with the first vector. Okay, now curl your fingers. Does that go to the R vector?
Oh, yeah, yeah.
No, only if you go all the way over, right? You'd have to like do that and I like, yeah. So that's not right. Try this.
This way.
Wait. That's not the DS vector. Here, wait. DS vector points to the right.
Okay.
So here, let me, here, stand, oh, here, walk closer to the board.
Okay.
Sorry. Right, so here it is, right? You get 4 choices, this, this, or that. Got it? So now, if you curl your fingers, did they go to the R vector? No. Try that one.
Oh,
You see it?
yeah.
So now, in that case, you go from DS to R, and then notice, this is tricky. That tells you the B field at this point.
Yeah.
So, yeah, show it one more time. R, DS goes to R, B field at P goes into.
Yeah. Okay.
Does that help?
Yeah, it does.
Yeah. Sometimes you just gotta kind of,
Yeah. Either.
here's a cool trick too, everybody. When you're doing these, you can move the paper so that you don't have to, you know what I mean? Just move the paper around and make it look good. Is that better?
Yeah. It's gonna be during the exam.
I know, it's always funny watching people like, they're like doing this, I try to do that every time. All right.
There's no glare.
No, let's leave it open all right, yeah, thank you. Well, I want to put this on. All right, I'm gonna put we'll see you guys in 10 minutes here.
Hey, Niles, you got your mic on.
All right, ready to get back into it, everybody? All right, I got a quick question for you. I'm gonna write down, this is just kind of a warm up. So here's an electric field equation. Here's a magnetic field equation. They're pretty comparable, but one of them, we basically have to integrate. This one, if it was a point charge, you wouldn't have to integrate, but, right? Or if you wanted to do the integral to make them look more similar, we just do that, right? DQ. Which fields tend to be bigger numbers? Obviously, bigger seems relative, but what do you think? What's that? Well, generally speaking, the numbers that we get when we plug in stuff into here, whoops, and let me get this on the main whiteboard, sorry. Right? One of these numbers tends to turn out much, much larger than the other one.
E.
Why?
K is pretty huge.
Yeah, what was K?
8.99 E9, I think.
Yeah, 99. Remember that? Forgetting the units. What was mu naught?
4 pi E -7.
Yeah, look at the difference in the constants. Do you agree? A billion billions of them or whatever. So now this is why we're only seeing these subtle little things where we're moving compasses and stuff. Interestingly enough, you may know this about light. Light is an electromagnetic wave, right? And this is a little bit hard to draw here, where we get these B fields going into the page and out of the page. And we're going to discuss this more at the end. But the idea here, even though the magnetic field is much weaker, it still has the same amount of energy in an electromagnetic wave as the electric field. So the values that you see don't necessarily directly correspond to energy density. So when you have an electromagnetic wave traveling, even though these numbers are going to turn out much, much smaller, the magnetic field will carry just as much of the energy in the wave as the electric field. That's just a fun side note. That's for later. It's foreshadowing. Okay, expect small numbers for these compared to those numbers because there's 10 to the -7 versus the 10 to the 9, forgetting the units and stuff. All right. Now, on the flip side, how about Q versus I? What are some typical charges we've talked about? What's Q for an electron?
1.602 times 10 to the -19.
Something on the order of 10 to the -19. So if we're talking about the electric field from this, well, you might say that's small, but then I argue if you have an electron that's going around in a circle like this, well, the amount of current is also very small. But so it depends wildly. The constant is not the only factor here. It's obviously the amount of source and the constant that combines. All right. That said, typically our numbers for current are somewhere less than an amp, maybe a few dozen amps if we have a huge current, right? Car batteries, trying to start your car, maybe 600 amps, but after that it gets pretty crazy, right? So here maybe we have nanocoulombs and the power drop out. You're still going to have 10 to the -4 or something. All right, good enough. Yay. Now, what's next? Problem 29.2. Now, I used kind of a non-conventional coordinate system here, so I'm going to try and draw this. I'm going to call this the X direction, this the Z direction. Which way is Y? Let's remember our wheel of pain really quick. I goes to J, goes to K. So if I want to figure out J hat, I could do K hat goes to I hat, goes to J head, right? Z goes to I, goes to end of the page. So since it's hard to draw, I'm going to draw it like this. Well, that's kind of goofy looking. It's hard to draw this one in 3D, isn't it? Now, I'm going to say we have a loop of wire here. So this is supposed to be my loop of wire in the XY plane. That's my attempt to draw that. So if we can understand how to analyze a circular loop, we'll be able to build up all kinds of different weird shaped wires out of circles and straight lines, and we can pretty much handle anything we want. All right. So to be clear, this is a circular loop with radius capital R. And our point of interest is right here. And we're told that this distance right here is Z, where Z above the center of the loop. And I think current's flowing this way, is that right? Yeah, all right. And then we also could look at a top view of this thing. Right? So the idea is, the reason I do this goofy coordinate system is, if I flip this up, what axis is this then?
Y.
That's the Y. So that's why I drew this screwy thing, so we could just view it as, if I look at it from the top, Y is up like normal. So here's our loop. And then in this case, current is flowing which way? Right here at the bottom of this loop, which way is current flowing?
Negative X.
That way, right? So, all right, so there's our current flowing around. Okay, our goal is to get V at P. That's our goal. Well, I'm going to write down my equation, the Biot-Savart law. And now I need to get the pieces so I can turn the crank. What's usually the first step? That's for straight wires. Perpendicular bisector is not for this one. If I want to do this integral, mu naught would be easy. 4 pi, I is just the current. What's the first tricky thing as we get along here? ds, right? We need to know where ds is before we figure out r, because r depends on ds. So let's pick a point right here. And I'm going to pick this chunk of wire. It's curvy now. You see that? What is ds? Maybe it helps if I draw it over here. It's this segment right here.
R d theta.
Yeah. Give me a second. This angle right here is d theta. It's a small amount of angle. It's not the whole thing. It's a tiny little angle. Now, obviously, I'm drawing it somewhat large just so I can actually fit this. But the idea is in the real integral, your d theta would be so small, right? It's infinitesimally small. And then what's the length? ds, the length without the vector. It's not your d theta, it's r d theta. Now, how do I get the direction? Well, in this case, what's the direction of a ds vector supposed to be? The direction current flows. So just tell me, clockwise or counterclockwise?
Clockwise.
clockwise, but that's not gonna work in our integral. So now, how do we describe clockwise? Now, be careful here. Yes, that's it, negative theta hat. Okay, so you beat me to it. This direction would be theta hat. This direction would be negative theta hat. So in this particular case, clockwise corresponds to negative theta hat. Good. If you didn't see that, I was going to come back to this picture and describe it. Because do you agree it's not going in the K hat? For torque, we use that when we're talking about torque, but that's a different situation. I don't want to go into that right now. Torque, you grab the axis of rotation and that tells you which way it's going to rotate. With this one, we're talking literally about which way things are moving or where their positions are located. K hat would mean out of the plane. It's clearly not ds, it's not r d theta in the K hat. It's around the circle. All right, so in this case, let's draw the r vector now, right? So I go which way? From what to what? From source to P. What's this distance right here? Now, do you agree we've got a lowercase r? I don't want to use the same r, so I'm going to use big R. All right, so what is the r vector in this case? How much do I go in the I hat? And it's negative. And then going up, we could write it this way. But would this be valid for the next line segment over, this one or this one? Would that r vector change? Would we still be going entirely in the I hat and K hat if we go to a different segment? No, so this is a terrible way to write it. What's another good way for this direction? Radially inwards. What's a good name for radially inwards in terms of a hat vector? Negative r hat. Now I'm going to use capital R here so we can keep track of. I'm going inwards. That's negative r hat. I'm going around, in this case, clockwise. So that's a negative theta hat. What do you think about all that? Am I losing anybody or is that okay? Okay. So now we can plug all this stuff in and I'm going to write this on the other board and then we'll go over to it. So just give me a second. Well, maybe I'll squeeze this in right here, right? We'll do this and then we'll go to the other board. B is equal to, I got a mu naught I over 4 pi. I've got myself a ds theta. Wait, what did we say it was? No, r d theta in the negative theta hat. So I'm going to write negative r d theta in the theta hat. That's my ds vector. I got a cross product and a fraction. My r vector was that. What is r cubed? What's the magnitude of that thing? And then we're going to have it to the what? So I'm going to pause there. Is that okay? So it's just ds cross r vector in this direction. Never enough time. Okay. Now, this is going to be pretty gnarly, right? But maybe there's some stuff that's constant. What in here does not depend on, well, what are we going to integrate over in this problem? Theta. Does the radius depend on theta? No, not unless you have an ellipse or something, right? How about z?
No.
That doesn't depend on theta. How about theta hat? Does the direction that you're traveling depend on your angle?
Yes.
Yes, do you agree? Here, theta hat would be, well, I guess we're talking negative theta hat. Negative theta hat here would be negative j hat. What about right here? Negative theta hat would be negative I hat. Here it would be positive. You see what I'm saying? Depending what you're, so this does not pop out. What about r hat? Does that depend on the angle?
Yes.
Yes. Radially inwards is this way, then it's this way. Do you agree? The size of it, remember, r hat has size 1, but the direction is toward the center. That's changing. So r hat can't pull out of the integral. Dang. It's gonna be a tough one, isn't it? It's almost like, man, I just wish we had another wheel of pain. Well, let's do this. Hold on. Oops. Okay. So first I'm going to start, help me out. What's the normal wheel of pain? I goes to J, goes to K, goes back to I. And if I could, I'm going to draw our coordinate system. Here's X, Y, Z. Well, now we're doing a new coordinate system, right? Right? We're at some arbitrary, this is hard to draw, we're at some arbitrary r hat, and then there's some perpendicular to that. This is really hard to draw, theta hat. But, and then up in the plane is z hat. Maybe if I could draw it this way. Let me try it one more time. Sorry, that's a bad picture. I'm going to make it look more like the calculus books, where they have this one, and there's this one. Right? And then you pick an arbitrary, whatever, we can code this up. But there's an angle here, theta, and there's a vector here, r. Well, r hat is 1 unit this direction, theta hat is perpendicular to it. And notice, r hat goes to theta hat, goes to up. Whatever. That's what I wanted to point out. There's a new wheel of pain in town. It's called cylindrical polar. Right, this wheel of pain also works. You can say r hat goes to theta hat, goes to k hat. Everybody okay with that? If not, too bad. Otherwise, we're never going to get this damn problem done. If you didn't believe me, I'll just point this out. If you wanted to prove this to yourself, the definition of r hat, and I should be careful here, aren't we using capital R hat? Sorry. If you recall, this is the definition of r hat in polar coordinates. And if it helps, this was the definition of theta hat. You flip the sine and cosine and make the first one negative. So there's lots of different ways to do this problem. You could first derive a new wheel of pain, which is what we just did. Or you could plug in the r hat and theta hat in these terms and do the integral, and it just sucks. Right? Because look how many terms you're going to get in this cross product. You see all that? That's not going to be pleasant. That's why I wanted to use this new wheel of pain. Okay, before I erase this and just do the integral, any questions? Okay, so if you need to know this, memorize it. Great. All right, so we're going to use this wheel of pain. What are you going to get here? Well, I got a mu naught I over 4 pi. There's my B field. There's going to be 2 integrals, right? Oh, do you agree I can pull out this basement?
Yeah.
That's better. Then, all right. I guess there's 2 terms here, right? Do you agree we're going to get there's 2 integral terms. I see a minus r squared times the integral of d theta times theta hat cross r hat. I'm trying to do this term right here. I got an r, wait, it's positive, isn't it? The negative signs cancel. Do you see that? Negative here, negative there. So it's r squared d theta, theta hat cross r hat. That's just the first term. Plus the other term, which is negative rz. Oops. We're running out of whiteboard. We are. Okay. Trying to do this term now. Oh gosh. That's good. Okay. We got negative r d theta, theta hat cross z k hat. Geez, I don't want to screw this up. Let's make sure I get all this shit in here. All right. We have a d theta. What else? Theta hat cross k hat. Is that it? Did I screw anything up? Negative RZ. Yeah, I think that's it. You agree? Woo! Yeah. You guys are having fun now. Well, help me out. What's this term? What is it? Negative K hat? Theta goes to R, goes to negative K hat. Absolutely. Sweet. How about this term? Theta goes to, so that's positive capital R hat. All right. So now, just doing the bracket parts down the page, we get an R squared. Wait, the negative K hat pops out. Do you agree? And this is just the integral of d theta. What are my limits? 0 to 2 pi, all the way around the circle. Okay. Now over here, I've got another term. I think it's that, right? Could I just pull the R hat out? What do you think?
No.
No, why not? What was the definition of it? Do you remember? This part, this is crap. I just erased it a minute ago, right? Didn't I? I should have left it up. Sorry about that. You agree that's our R hat? Huh? What are our limits? 0 to 2 pi. And now I'm going to go over to this board. What are you going to get when you do this integral?
Theta.
Cosine theta looks like this, right? What do you get when you integrate a function? You get the area. What are you going to get when you integrate cosine theta from 0 to 2 pi? 0.
0.
Yes, good, good. Does that make sense?
Yeah.
If you integrate cosine, you get as much area above and below. Well, what are you going to get when you do sine? That one's easier to see. Do you agree? Don't you have the same area above and below? So what are you going to get when you do this integral? So what happens to this entire integral? Good. And what did we get when we do this integral right here?
2 pi.
2 pi, yeah. Got it? We're finally done. You can move on with your life now. Let's put all this in here. What do we get? We're going to get a 2 pi. Do you agree that's going to cancel 2 and pi? So I'm going to get mu naught I over 2. Now there's still an r squared left. There's a negative k hat in this case. What else? There's what, r squared plus z squared 3 halves, is that what's left? Woo! Gnarly. Well, just like the straight wire, we're going to use this result a lot, and hopefully you don't have to derive it a lot. Okay? So I dragged you through the derivation, so maybe you would appreciate it. This is one of the equations that's on your, we should take a second to look at your exam equation sheet, and I'm looking down here, somewhere right around here, right in the middle. You see there's something that says B solenoid, B ring, and B straight. There's your different formulas that we just derived. So those are on there. Got it? Sorry, it's my book's getting beat up. Well, a common formula that I usually ask for is at the center of the circle. So if I could, come on. If I want to get the B field at the center of the circle, how can I quickly get that from this formula? If I want the center of the circle, Z goes to 0. Look over here at this formula. This formula, B center, and let's just get the magnitude for right now, okay? Screw it. If B center means set Z equals 0, what do you get when you set Z to 0?
Or cubed on bottom.
You get an R cubed, but then you have R squared on top. What are you left with? And then there's the, how about I just put question hat for the direction? You know what I mean? Like you could decide this. Ooh, that kind of begs the question. How could I check the direction here? What's that? Right-hand rule, right? So we had a loop like this. We had a Z direction. The current was flowing this way. I grab that wire. I curl my fingers. Notice my thumb points negative K hat. Now, all right. So far, so good. Pretty gnarly, huh? I don't know if this helps you, right? You've got the formulas on the back of your equation sheet, but I just have these memorized by this, right? This is a circle. There should be a pi in it. There's not a pi in it. Physics is hard. They're trying to trick you. Or, where is the pi hidden inside of here? Mu naught has a pi in it, doesn't it? And then think about the straight wire. The straight wire looks exactly the same, except it has 2 pi on the bottom. Well, the 2 pi on the bottom would cancel the pi inside of there. So if that helps you, whatever, or just look it up each time. Look it up on the table. All right, now let's have some fun with this, and then we'll just do one more question, I think. Yeah, let's do one more. Oh, gosh, I just wish I could be faster. I don't know. Is this too slow for you guys? Should I go faster, or is this about right?
It's about right for me.
Yeah, right. If I go any faster, we end up getting lost, right? So it's just about the fastest we can go. Some of you might be able to go a little faster, but most people, it's about right, hopefully. I want to show you how this can be fun now. You've done the work. Now we get to have the fun problem. All right. Let's look at 29.3. Got a wire coming like this. Then it takes this 60-degree bend. About like that, maybe. Not very perfect, but close enough. We're told this is 60 degrees, right? And then it's going to come off here and do some other monkey business. Like this. Is current flowing that way? No, the other way. This way?
Yeah.
All right. So now, well, I see 3 wire segments. Do you agree? I could number them however. I'll just call this 1, 2, and 3. The idea here is what we want to do is figure out B net, right? I don't like that blue. Let's get another blue. Oh, yes. Do you agree we could just add up the 3 contributions from these segments? That's our goal. So now let's start with segment 1. If we could just figure out what B1 is, we're good to go. Well, should I be using straight lines or curved lines for segment 1 if you had to guess? Straight, it's a straight line. What do you think the answer is? What is it? What is it to you? U naught I over 2 pi a. This is the field of a infinitely long wire. Well, does the problem say this wire is infinitely long? So is this an infinitely long wire? No. It's half infinite. This is what the perpendicular does. So the straight wire says, aha, isn't this a right angle right there? So this corresponds to half of an infinite wire, the left half of it. This is very different. So when we're using a perpendicular bisector, that's our reference point. This is half of that. So shoot. What do you think the B field is of half an infinitely long wire? Times it by a half. Ding, 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 ding. Why is this equation not correct yet? No direction. What am I going to do? Grab that wire. Oh, and I should be clear. In the problem, wasn't this distance A? I want to make sure. Oh, shit. Okay, so this is distance R. So this is not A anymore. I probably need to use R right here. Do you agree? Okay. Grab that wire. Above the wire, what direction is the B field? Negative K hat into the page, right? I guess we're assuming here that this is I hat, this is J hat. I'm going back to our stamp. So notice what Christian and we had some disagreement there. It's because we hadn't drawn a coordinate system. So generally speaking, we should get our coordinate. That way we're on the same system. So is everybody okay that above the board, it's into the negative K hat and below it's positive K hat? Sorry about that. You were using the last problem's coordinate system. I started a new one in my mind. Okay, sweet. How about B2? Feel like we're playing bingo. B2. Any guesses how I'm going to pull that one off?
You use the one for the ring, but divided by 4.
Nope.
What? Or divided by 2.
Nope.
I don't-
You're close. How much of a circle do you have?
Oh,
60 degrees is how much of a circle?
Quarter.
Sixth.
Oh, God.
1/6 of the B field. Now, I'm at the center of a circle, right? You can imagine it here, but we're not really, we only get 1/6 of the contribution. All right. So now, what was the formula for center of a circle? For you guys on Zoom.
Mu naught I over 2R, negative K.
That one, right? So, right, we're in the plane of the loop, so we have z equals 0 for this problem. So we're using this lower one, not this upper one. Isn't this so much nicer than those integrals? I just love this part. It's fun. Well, I have a strange definition of fun, as you know. What's the direction? How do I figure out the direction for a circular loop? Which way is my thumb? So which way is the B field? Positive K hat. So far, so good? Isn't this more fun than all that painful integration? I like the painful integration, but this is even more fun to me. All right, B3, what do you think? Is it going to cancel out B1 or not? How do you know it's not going to cancel out? Oh, let's see. What's the size of the field for B3? It's infinitely long, so should I use an infinite wire? It's half infinitely long, right? I'm just trying to trick you again. Do you agree this is the perpendicular bisector? So again, it's half of the infinite wire. But it does use the same distance as this other one. What's the direction? Grab that wire. So at this point, which direction is it? Out of the page, right? Do you agree we could just add these up now? Well, do you agree 1 and 3 combine to make one infinitely long wire? And maybe now that makes sense to you, right? Isn't this basically like an infinitely long wire plus a little section? And so now we see that that half infinite does make sense in this weird way. Don't let me forget. I don't want to forget. On page 152, could you write down page 21? So I'll talk about that when we're done. I just want to mention page 21 has some tricks. I need to put it here. All right. Okay. Do you agree here? It's basically going to be mu naught I over R in the K hat times some number with 3 sig figs. We're good to go. Right? You're just going to add up all these little fractions. So here you get a 1 over 4 pi. Here you get a 1 over 12. And here you get a 1 over 4 pi. So I guess if you wanted to, you could just write it. We get a 1 over 4 pi plus a 1 over 12 plus another 1 over 4 pi. And then you can convert that to a number with 3 sig figs. Now, if you're a physicist, you'd obviously just leave it in this form and simplify it that way. But everybody else just grabs a decimal because it makes more sense. Right? So, cool. All right. Never enough time. You like that move, Jose? You come to office hours, I have to leave. I say, oh, we'll answer it in class. Then we go through class. I'll answer it at the end of class. And then we know to have time. If you want, do you have something to get to right after this?
Not really.
Because I can help you right after class if you want to.
Okay.
All right, if you're not tired. So, yeah, I had to do an eval for another prof today, and so I forgot about it. Missed office hours, and he came then, and now I blew him off twice. That's a man. Blow you off one more time, I'll have to give you an automatic A in the course, right? Yeah, right. Okay. Well, just to keep it all together, we're doing a lot of BS today, right? This is all BS law. I want to show you one other style of question. We got 6 minutes. We're going to pick up here next time, but I just want to foreshadow it. All right. So look at, if you could, open up and look at pages 154 and 155. Just have them sitting out there. Okay? And I'm gonna erase this board while you're looking at that. Some of those problems look like what we just did, but a couple of them don't. So I want you to look at that page and see which kind of problems look like the ones we just did. Maybe you could imagine trying to do them. You see a lot of straight line segments and curvy segments, and you could try and piece together different calculations in terms of the straight and curved segments. Which problems don't look the same? Which problems look totally different? Two of them. Which ones don't have straight lines and curvy lines in them? I'll show you one. Look at 29.4. Do you see we don't see straight line and curvy lines in there? We do have straight lines in the word problem in the pictures, but I just want to point this out. Let's say I have some problem like this. All right. Here's the deal. Imagine you have two straight wires coming out of the page. I promise we're going to pick up here next time, but just give me your attention for a minute. There's two straight wires coming out of the page. If it helps, you could imagine this. Right? These two pieces of brass, right? The idea is we have really long wires. So if I'm somewhere in this region, right, I'd have these two really long wires coming out at you. All right. Now, maybe what I'll do is I'll color one of these, any other color. And let's label this one 1, and we'll label this one 2. Well, I'm going to grab that wire. This is that wire, right? I'm grabbing that wire. Again, this wire is coming out of the page. I'm going to grab it like this. Notice the B field is going to curl around in a circle like this. That is the radius vector for number 1. And which way does B point? Around in a circle. It's always perpendicular. That's the direction of B1. Well, now I can come over here and do B2. This would be radius 2. That would be B2. And I would get 2 vectors to add up. This is the equivalent of point charges. Do you see it? When we went back to point charges, didn't we have electric field 1 plus electric field 2, and we'd add up 2 vectors using SOHCAHTOA? That's what we're going to do next time. Okay, so we've seen that you can use calculus or these shortcut tricks, the splitting things into pieces, or going up next time. Let me just zoom backwards. Right? Oh. Right, so we saw that you can use tricks where you split a wire into segments and add up the pieces of straight and curved wires to get the total magnetic field at some point. Or next time, we're going to revisit this where you have just a bunch of straight lines, infinitely long, and then you can get the B field from each contribution. And we're going to see these right angles popping out. That's for next time. All right. Any questions? Get out of here. All right. And then I'm going to get your questions if you want. Oh my goodness. Give me $1 million, please. Y'all good on Zoom land there, people?
Tell me it gets easier.
Well, we did these long derivations. For the most part, I don't know if you're going to have to do too many straight wires. I think there's only one question where you really have to work too hard at it. I hope that learning how to do the angle trick will make it easier. It should get easier eventually.
Yeah, that wasn't too bad. I feel like just with practice, it'll get easier.
Yeah. And you know what's nice? If you notice, there's no non-uniform here.
True.
So the current is always popping out of the integral. So at least that's one less thing to deal with. We got the cross product in there, but we don't have non-uniform stuff now.
The non-uniform will be on the test.
Well, no, not for, well, remember, this is all for test 3, right?
Yeah.
Yeah, so the non-uniform will come in a different part of this chapter.
Okay, so it does get worse.
Well, you remember Gauss's law? Did you like Gauss's law?
Indifferent.
Well, basically, this was the magnetic equivalent of chapters 21 and 2.
Right.
Next one is Ampere's law, which is the magnetic equivalent of chapter 23, Gauss's law.
Okay.
So that's the last half of this chapter. So we'll probably get to that after the test, or maybe start it next time and then or foreshadow it and then finish it next time. Is that good?
Yep.
All right, man.
All right. Have a good one.
Yep. All right, I'm gonna call it, Zoomers.